Just a brief profile about Engineer Victor Nwokolo. He is a chartered electrical engineer with a proven experience in the design and engineering of electrical power systems, project management, and power system studies. He has a background in electrical maintenance. He's experienced in conceptual FEED, FEED, and detailed design of electrical power systems for offshore and onshore facilities. He's currently consulting for PBS by Ponticelli Aberdeen on the Total Energies contract and Navante Oil and Gas Company Limited, Lagos, on various projects. Engineer Victor holds a BEng and MEng in electrical and electronic engineering from the Robert Gordon University in Aberdeen. He also has a national diploma in electrical and electronic engineering from the Petroleum Training Institute, PTI. He has several professional certifications, including being a chartered engineer with the UK Engineering Council, a registered engineer with CEng. He's a member of the Institution of Engineering and Technology, IET, and of course, a corporate member of the MNSE. I invite and hand over now to Engineer Victor Nwokolo for his presentation on the role of electrical protection system in ensuring reliability of power distribution. Engineer Victor, I'll just stop sharing and over to you. Thank you.
Thank you very much, Emmanuel. Thanks for this opportunity. Before I start, I just want to acknowledge the presence of the following, the outgoing chairman, and Dr. Sheon, and the incoming chairman, Stephen Wang. I want to also acknowledge the outgoing executive of the Glasgow branch of the NSE and the incoming executives as well. I'm not sure who other dignitaries here, but I just want to say all dignitaries are duly observed. Thanks and welcome to this presentation. Thank you very much for the introduction. I'll share my screen now, sorry. Please let me know when you can see it.
Yes, can see it now.
Okay. The topic of our discussion today is the role of an electrical protection system in ensuring reliability of power distribution network. This is something I initially wanted to focus on the industrial power distribution, but during the preparation, I decided to have a touch of the Nigerian power distribution system. So you're going to see a mix of offshore industrial and utility power distribution in the course of discussion. Because of time, I had to take off the icebreaker, but I know most of us—
Meeting don't start.
Okay, most of us did physics and first year engineering science, electrical engineering science. And our basic knowledge of electrical engineering or electricity has to do with three components, which are the electrical current, electrical voltage, and resistance. So with these three, you can have electrical power and the rest of the elements that make up electrical system. So I'll go with some basic terms, basic definition of terms. So first here, I just want to introduce us to most of the terms we'll be using during the course of the discussion. And starting with what electrical power system is. Most of us know this, but just for the benefit of everyone. So it's a network of electrical components used to supply power. And when I mean supply, I mean generate, transmit, and distribute electrical power to consumers. So where you've got power distribution, power generation, and power transmission together in a localized region, we call that electrical grid or electric grid. So that is basically electrical power system that supplies power to homes and other industrial consumers within a sizable region. And we have components that make up a grid. looking at the generation, transmission, and the distribution components. And today we're looking at the distribution component. So that brings us to what a power distribution network is. For the sake of definition, is the final stage of an electrical power system. And it's basically this, the stage where power is taken from a distribution substation to the final consumers, which may be residential, commercial, or industrial. So in Nigeria, the distribution system is a mix of two methods of transmission, the overhead and the underground cable transmission. So looking at the distribution network, we've got, according to the Nigerian distribution code, the voltage levels that make up the distribution network ranges from 230 volts single phase to 400 volts three phase. These are low voltage, to 33 kV high voltage. So this voltage range forms the Nigerian distribution network. In other countries, this varies. In other, like in the industrial setup, it varies as well. Like an industrial setup, low voltage is primarily for distribution, except for where we've got some high voltage consumers like export pumps and some VSDs that operate at around 3.3 kV, 6.6 kV. These are specialist load. So in the Nigeria context, it ranges from 230 volts single phase to 33 kV high voltage three phase. Then in the course of our discussion, we'll be looking at power system reliability, and this is basically the probability that a power system performs correctly during a specific time duration. It is also the degree to which electricity is being delivered to consumers within acceptable standard. That's very important because you can supply power, yet it's not reliable. If the voltage is too low or too high, that means it's not usable. So that power supply has to be within an acceptable standard for it to be considered reliable. Also, we'll be looking at, we'll be touching on power protection system. It's basically the arrangement of power protection equipment and other devices that are required to detect and isolate electrical faults in a power system. Also, we'll be looking at fault, and fault happens to be any abnormal condition that affects a power supply within a power system. For instance, we'll be touching more on power electrical system faults. So that will be on the next slide. Expanding more on electrical faults. Fault ranges from visible to non-visible faults. So in the course of a definition, we'll be looking at faults around overhead system and faults on underground system, and we'll be looking at the various faults that exist there. So we'll be looking also at the types of faults. So what are the types of electrical faults? We have, for the sake of summary, the electrical faults are within overcurrent and voltage variation. Everything else, should I say, is a variant of these two. It's either you get overcurrent, undercurrent, over voltage, or under voltage. Everything else, every other fault in the electrical system is a variant or is derived from this. So we look at the most common ones, types of fault we've got. So we've got faults like overload, and this is considered a sustained overcurrent under 200% of the rated current, except for motors. And why I say for motors is because sometimes during motor starting, you can have overcurrent or overcurrent exceeding 200%, yet is classified as overload. at that point. So we'll talk more about it. And overload is something that eats up the conductor or the current carrying element of any electrical system, thereby producing heat. So the heating effect is what causes the damage. And we'll look at how to protect against overload in the following slides. We also have short circuit. Short circuit is another very rapid and very common form of overcurrent. It exceeds 200% of the rated, and in many cases, it occurs where two current carrying conductors come in contact with each other. And because they've both at different potentials, you get a reaction between them. And this is due to the electrical phase between the two potential carrying or voltages, if I put it like that. So short circuit is a common fault of a common type of electrical fault. We also have earth fault. Earth fault or ground fault in America is another type of short circuit. But in this case, the short circuit also extends to ground. And where you've got like a short circuit that makes contact to ground, we call that earth fault. And the reason why I separate them is because we protect against them differently. We protect against the normal short circuit between phases differently from how we would protect against the earth fault in an electrical system. We also have open current or open circuit, sorry. Open circuit is where we lose like a phase of a balanced three-phase supply, where all of a sudden the system becomes unbalanced. This is mainly like, in some cases, we experience this where we have like a mechanical damage and cut off on a power cable, or we have a sudden fuse blown on a three-phase line. And as a result, we have an imbalance in the system. So as a result, we get an open circuit fault. Then we also have other faults, such as over temperature, undercurrent. We have under frequency, partial discharge, and arcing fault. Also, there are also some faults that are classified as lightning surge. We'll look at that as we go ahead. So, fault in distribution system. In a distribution system, we basically have faults classified as temporary or permanent. In the temporary distribution system, we say when a temporary fault occurs, equipment used to supply protection operates to isolate the fault. A transient fault in a distribution system will then clear the fault. Where that fault fails to clear within a short time, it can easily transit into a permanent fault. An example of that is if a fault is not cleared off a line, a fuse is blown, and where we now have to carry out a repair on that line, it becomes a permanent fault. So it's a simple transient fault that would have been cleared by a correct protection device within a few seconds can easily become a permanent fault that will require a repair team to be dispatched to that to locate the fault. And this happens when the protection system or the protection devices or the protection scheme is not correctly doing its job. So we'll touch on that when we're looking at how to clear faults. So let's quickly look at power distribution system protection. We just want to look at the objectives of power distribution protection. The main objectives, one is to maintain reliability of running power system. The other one is to eliminate safety hazard as fast as possible and to protect equipment from getting damaged. These are the three main objectives of a protection system. And in order for us to achieve this, we have to keep some things in mind. Two things in mind, basically. We have to make sure that only the faulty part of a system is completely isolated within minimum time so that the remaining system can operate normally. We also have to keep in mind that in normal condition, there shouldn't be any nuisance stripping when we're designing protection against fault. And then there are some functional requirements for protection system. And these are basically 5 requirements to consider when designing a protection system. One of them is reliability. We say that the reliability of the power protection system, the protection system must have the ability to operate and correctly when called upon in the event of a fault in a power system. So 1, it must be ready to operate, and 2, it must operate correctly, and that gives you the reliability. The other thing to consider is the selectivity. It is where the system, we can say the system should have the ability to avoid unwarranted trips, like what I mentioned earlier. So it should be able to only isolate the part of the power system that is faulty or where the fault occurs. Then also it should have speed, and it should be able to operate within a specified time in order to avoid damage. And 2, it should be able to know when to operate. That is something it must consider as being sensitive. So we say in the sensitivity, it must have enough sensitivity within the design to be able to operate reliably at the correct condition of fault. If, for instance, you're starting a motor, you don't want the power system to operate within 200 seconds as picking it up as overload, or when it exceeds 200 seconds, you don't want your short circuit to kick in. So you must design it correctly so that it's sensitive enough to avoid unnecessary trip. Then the final thing there is the coordination. Coordination is basically like taking all 4 of the earlier requirements into account. That is the reliability, selectivity, speed, and sensitivity into account. So when all of these are correctly designed and operating in the correct manner, then the system is coordinated and correctly coordinated. And it also allows us to operate a system correctly. And coordination also look at the equipment itself, making sure that the equipment don't get damaged. Like when you put in the speed, in your coordination, you take the speed of the protection system into account. So that is, sorry, I can hear some voices. I'm not sure with some mute.
Apologies. Can we keep our microphones mute, please? Thank you very much. Please continue, Innovator.
Okay. So yeah, coordination takes into account all 4 functional requirements for a protection system, and this helps us to give a proper protection scheme against fault. Just some quick look at equipment we use for protection system. 2 of these are basically protection device, and the other 2 are other devices that support protection system. And the 2 protection devices there are protective relays and fuses. Instrument transformers and circuit breakers are considered other equipment that are used in a protection scheme. For instrument transformer, let me just, a quick definition of an instrument transformer is current transformer and voltage transformers. These are the element of a protection scheme that reads the current and voltages of the power system and pass that information to the protection relays. The protection relays monitors that current flowing through the system and the voltage within the system against a set within a predefined setting. And if that current being read is abnormal, and the protection relay picks like the current exceeding the predefined setting, it sends a trip signal to a circuit breaker to say trip, because it has picked up a fault. But for a fuse can also sense at the same time, can trip on in the presence of fault. So fuse is does the work of both an instrument transformer, a protection relay, and a circuit breaker in a protection setting. In low voltage a system, some circuit breakers can also do the job of sensing and tripping. And that, for instance, where we have things like a thermomagnetic property of a circuit breaker, it can sense for overcurrent as well as sense for overload in the system. So a circuit breaker and a fuse can do the job of sensing and tripping in some system, especially in a very low voltage system. Protection of power distribution system. I'm just going to touch how we protect against those various faults we looked at earlier. Protecting against overload, and overload typically operates in inverse time curve. That is where tripping becomes less as the current increases. So your overload is where you have like, say your current set for a breaker is 6 amps. If for any reason, due to demand on the other end or due to improper design, the load side is pulling in maybe 6.5 amps. The protection device will see that as an increase over the 6 amps that is rated for. And we continue to monitor this for a period. And if this continues to stay, the heating on the system will increase, and at some point, depend on how much overload allowance you've set in the system, a fuse or a breaker will trip to cut off the overload, because overload can easily damage some of your systems, especially cables, and also can eat up some components within your electrical system. So in order to avoid that, if overload is seen for a prolonged period, then the protection device will cut it. So the common type of protection equipment we use for overload are overload relays and thermal circuit breakers. The thermal circuit breakers senses the heat rise on the flow of current and trip it. Some slow blown fuses are used as well. This is because they monitor the slow rise in current for a period, then they react. Then the next thing is short circuit. Protection against short circuit. So a short circuit, as I explained earlier, is a rapid overcurrent that occurs because of two potential differences meeting together, like you have voltage from different sources, not on the same electrical phase difference, meeting together, so you get a reaction. So when that occurs, you get a massive surge in current there, and that creates a magnetic property around the area where that short circuit has happened. So some circuit breakers will pick that as a magnetic rise and will trip the breaker, and fuse will pick that up and trip the fuse. We also have overcurrent fuses, which are specifically designed for that. It sees that sudden rise in current and initiates a trip to kill off the circuit. Then we also have earth fault. Like I said before, earth fault is a type of short circuit, but because it requires a different protection. That's why it's separated here. So we have earth fault, and the common equipment we use for earth fault are earth fault relay. They specifically pick the flow through to earth. And we also have earth leakage breakers, as well as ground fault interrupters. These are used in power transmission lines or distribution lines. And what they do is they tend to restrict the fault current to earth, and that kills off the fault. Then we also have protection against open current. Open current is specifically doesn't have a defined protection, but it can be monitored in a controlled distribution where we have some sensors or detection equipment in the line that measures the balanced three-phase. If for any reason we have a drop of one phase, it picks up a zero sequence voltage, and that sends that information to the system. In some cases, those systems are further automated to cut off the supply. So over open circuits is considered a fault because in a distribution system where you have three-phase supplies, if we lose one of the phases, that means a section of the consumers will lose power. So you want to monitor that, and that's why it's considered in a distribution system. Other faults to look at are over voltage and under voltage. I'm just looking at time, so I have to rush through, sorry. Over voltage and under voltage, we use special equipment for over voltage. Apart from the lightning surges, the internally derived over voltages are not big enough to cause issues to a power system because most insulations are around cables and equipment, winding coils, and the rest are, and they are designed well enough to be able to accommodate up to 2 times the voltage level. So that it can only become a problem where the system is not properly designed. Under voltage, we use relays to sense the under voltage, and the correct protection acts and either cut off the circuit through breakers or fuses. Protection against under and over frequency. This happens where we have loads, sudden drop in load or sudden drop in generation. So if we have sudden drop in load, we have a surge in the power system because the demand all of a sudden drop. So the supply becomes so surplus, the frequency vary. And the opposite is also the case where we have a sudden drop in generation. Maybe you have 3 generators, and all of a sudden one drop. That means you lose a section of your load. That we protect against frequency, under frequency there, and use things like recloser to cut off a section of the supply and let load shedding take place in order to balance the load. Lightning surge and arcing faults, these are also common in power distribution, and they are protected using interrupters, circuit breakers, and specially designed protection relays. I'll skip this. The electrical Nigeria distribution code is just something that has been enacted to protect, specify how power distribution is supplied in Nigeria. Because of time, I have to skip that. There are technical requirements on section 4, and it tells us how we can protect our distribution system in Nigeria, but I have to skip that, sorry. Improving reliability in a power system. So there are a few things I picked up, I just feel we should look at. One of them is to improve available power from the grid. So if power is surplus from the grid, we have reliable supply. And we also investing in distribution equipment, where we now bring in some smart distribution equipment. Then we also look at the possibility of investing, especially for new supplies, investing in underground power distribution. This will improve a lot of power reliability, because most of the faults we get on overhead system can be eliminated through underground distribution. So improve maintenance and operating culture. We need to look at improve the way we maintain our distribution equipment. In Nigeria, I can see in many feeder pillars, instead of a suitably rated fuse, sometimes they use wires as fuse, which is very bad because one, it has safety implication, and two, it kills the equipment because you're not giving the equipment proper protection. We also have to look at the culture of protection audit. This is where we carry a site review of our protection systems on a distribution network. We also look at the distribution management system, looking at training and retraining of the field technician, very important because that ties into the maintenance culture. They're looking at investing on smart power distribution. This is where this distribution system can be monitored and anticipate fault before it even happens in the distribution system. I'll quickly move forward. Improving reliability further. I'm looking at how effective protection helps there. One thing we'll aim to do is to reduce permanent fault through proper protection system. And this is done by the use of two very common equipment in the advanced world. In Nigeria, this is not very popular, but if these two equipments are introduced into the Nigerian distribution system, that would help a lot. And one of them is recloser. Recloser is a type of automatic circuit breaker. It's designed and placed at intervals on the distribution network overhead. What it does is, if there's a fault, especially a transient or temporary fault, it senses that fault, it trips the system temporarily, waits for a few seconds, then try to re-engage it. If that happens, the fault is still there, it drops out again. It does this for a predetermined number of times and for a predetermined duration. And it causes the systems and drop the network out, in and out. If it continues and the fault persists and maybe the system assumes it's a permanent fault, a different device called sectionalizer come in. And what that does is, when the recloser is in the open, when the recloser is in the open state, the sectionalizer break the circuit. So you just keep that section, that small section of the distribution network open until a field technician goes there. So when it does that, the recloser recloses again. And when it closes, the sections that are unaffected by the fault will still remain with power, while the small section, the sectionalizer course of, is the one that will remain for field technicians to look at. Then my final point here, we also have to look at proper coordination, and there are a few criteria for coordination. And coordination, like I mentioned before, is where we look at how the entire protection criteria are carried out. And then the basic criteria to be employed is the main protection should clear a permanent or temporary fault before the backup protection operates or continues until the circuit is disconnected. Loss of supply caused by permanent fault should be restricted to the smallest parts of the system for the shortest time possible. So we have various types of coordination. We have fuse to fuse, fuse to recloser, recloser to recloser, recloser to relay, recloser to sectionalizer, recloser, sectionalizer, and fuse. Because of time, I can't go into each of these. So that brings me to the end of my presentation. Sorry, I have to rush through. The time is too small for this. Thanks very much.
Thank you very much, Engineer Victor Nwokolo. I think that's a very highly loaded presentation, and you've done justice to it within the allocated time. Thank you so much for this. I hope you'll be able to provide the slides. A couple of people would want to have copies of the slides. Yes?
Yes, I can do that, but I have to add the references to it. So yes, they should give me a couple of days.
No problem. So we'll be opening the floor for questions and answers. Engineer Sharp is not here, so I'll just coordinate the questions and answer sessions. I see a hand up already. Please, if you have questions, feel free to signal by raising your hands or dropping the questions in the chat box, and then we'll take them. It's been a wonderful over 30 minutes now of talk from our presenter today on reliability in electrical systems. He's talked about building in redundancies and coordinations and all of that. And yeah, we expect lots of hands. So 2 hands. I'll start with the incoming chairman of the branch, Engineer Stephen Ubonyi, himself an electrical and electronic engineer. Engineer Stephen, you're mute.
Thank you, Engineer Emmanuel. So, Engineer Victor, thank you for your wonderful presentation. So, I think you did actually cover a lot from the equipment side of things. So, my first question would be, how do we apply reliability to power distribution networks? Because I think I'm speaking based on my experience. I work for Strathlight Power Networks Demonstration Center. We research, design, test, and evaluate, and we work with DNOs. So I want to find out, mostly I think it's actually based on communication infrastructure, interconnecting these substations, power systems, facilities, infrastructure. So I don't know, based on your experience, if you have if you can comment on if these faults do have any impact on security of power networks in terms of ISO 27001 standard and the IEC standards. If you can comment on that, please. Thank you.
Okay. Yeah. So your question is, I'll take the first part of it. You said, how do we improve reliability in the distribution system? I believe, is that the question?
Yes. How do we apply reliability to power distribution networks? So I think it should be from the comms infrastructure. This is my understanding. The comms.
Okay, comms. Yeah, okay. Okay, if I go back a couple of slides. Yeah, I try to give some in the Nigerian context, but in the industrial concept, that should be much easier, because most of the issues we get in the overhead distribution network should not be present in an industrial setting. For example, if your substations are within urban areas, we believe it will be an underground distribution of power. And in that case, it eliminates your temporary fault altogether, or to a very large extent. And temporary fault accounts for 75 to 90% of the faults we get in distribution. So you're left with 10%. And these are issues that would then be handled with proper design. Example of them is making sure you carry out protection audits. Like I stated, if the protection audit on the systems on those substations are regularly inspected, maybe through site surveys, you will pick an insufficient power protection. And as a result, you anticipate the unreliability of your protection system in the case of a fault. And if you have proper power distribution network management. So 2 things we look at there. One of them is outage management system. So this provides data and information from various sources about fault, allowing maintenance engagement of workers. And you can also have an asset track record of facilities. So you know how your equipment are aging. If you're having deterioration in your equipment, maybe you're having a faulty cable where water ingress can go into a cable and cause a short circuit or a breach. Through proper management, you can eliminate all of this. So proper management and protection audits will eliminate most of the faults and improve your reliability in those set of application. I don't know if that answers your question.
We can proceed. Yeah, thank you.
Okay.
Thank you. Thank you very much. So I'll call on Engineer Sani M. Lawal. If you could unmute yourself and ask your question.
Yeah, thank you. I don't know. Can you hear me?
I can hear you.
Yes.
Yeah. Wow, that's wonderful, Engineer Victor. In fact, you took us around the power system from generation down to distribution, which is really wonderful. Yeah, my question goes this way. One, you made mention of a standard single phase in Nigeria. Is it
Sorry,
230? Sorry, can you hear me?
I can hear you now. You went a bit
Okay,
quiet.
okay. Sorry, the standard single voltage in Nigeria, is it 230 or 240? Which one is
Yes,
more
it's
correct?
230.
230, good.
Yeah,
So then,
okay, go ahead.
okay. Then, since you are working in the UK power industry and with your experience, I don't know, what is their reliability indices, the UK power system? Because I know they are being rated based on the indices globally. Each country has its own. For Nigeria, I don't know, we don't even belong to the club because our own cannot be placed anywhere to close of having the indices, really. And then, as mentioned by my incoming president, Engineer Stephen, generally reliability, it has to do with sensitivity of protection, how the system responds. And I believe Dr. Victor has brought the issue very well, bring out different factors of what brings reliability. So for any power system to work, I mean, to sense any fault and take action against it, that's what brings about reliability of any system. And definitely coordination is very, you thank God I've seen different coordination system you brought in, which is highly wonderful. Thank you so much for this presentation.
Thank you very much, Sani. On the voltage, yes. When we add the harmonization of voltages, I think I'm not sure if this 2007 Nigeria adopted that. I will double check the date, but Nigeria adopted the IEC harmonization of voltages. Before then, Nigeria was 240 for single phase and 415 for three-phase low voltage. And when when the UK was also the same at before the IEC harmonization. So when the harmonization kicked in, the UK accepted 400 volts three-phase and 230 volts single phase. And the three-phase was the single phase 230. If you multiply that by √3, which is 1.732, multiply 230 by that, it gives you roughly 400. And that's where the 400 volts three-phase and the 230 volts single phase kicks in.
Thank you so much. The reliability indices?
Yes, I don't have the number on my head, on top of my head, but the UK does a regional grid system where they have a grid, like for the Scottish part of Scotland, they have a separate grid from north of England. So these grids, though they have interconnections, each of these grids have their own specific indices, but on overall, I know the reason why the UK reliability is high is because of the urban area underground distribution network they apply. And we only have rural areas where we have overhead. And if you, what happens in the rural area is when there's any adverse weather condition, it affects it so much. We hear of power line dropping, we hear of short circuit, and having a section of the population out of power for a period. And that shows you the difference. It's within a country, you could see if there's storm or if there's snow or wind, the urban areas will still retain power, while the or the rural areas will be out of power for days until those fallen infrastructures are repaired. So that is one advantage over underground has over it. And the UK indices is because largely they are operating the underground power distribution. I'll get the numbers for you later.
Thank you.
Thank you so much. Thank you so much.
Thanks very much. Because of time, the two hands are already up. I think you just ask your questions very quickly, And then I'll encourage the presenter to also answer it very quickly. Now we have 3 hands. I would start, as I saw the hands come up, from Engineer Folabi, and then Engineer Tasiu, and finally Engineer Bashiru. But please make it very, very brief. Engineer Afolabi. Engineer Afolabi Adeosun, if you want to ask a question, unmute yourself.
Oh, sorry, I was on mute. I do apologize.
Right. Okay.
Good afternoon, ladies and gentlemen. And thank you, Mr. Presenter. My question is very basic. It's on, we talk about reliability. But when I was involved in what they call RAM in those days, long time ago, I was of the opinion that the key thing we need to look at is availability. So when we're talking about reliability, what is the availability of the system itself? And how does that relate to the reliability?
Okay. Availability.
If you just hang on, Victor, so we just take the 3 questions and then
okay, no problem.
Yeah. So Engineer Falabi is saying the relationship between availability and reliability. Engineer Tasiu, your question. If you unmute yourself. Engineer Tasiu. Okay, I'll move on to Engineer Bashiru Muhammad. Can you unmute yourself and ask a question? Yes.
Okay. Good evening, my honorable colleagues. My own is not a question. I joined the almost the end of the program. Can we get the presentation, please? I am from Engr Power PLC, the biggest power station in the country. That is Engr Krodu branch. I'm from that branch of engineering, MNSE. Thank you very much.
Very good to have you with us.
Yeah.
I think.
Sorry, Dr. Ma. We'll try and if you keep eyes on our websites, and that can be easily downloaded through our website.
Okay, that's good. Thank you.
Where we call, sorry, Engineer Ma, where we call Engineer Tasso, I believe that's my president. That's is that the president of the Nigeria Society of Engineers, Engineer TSG, UD, FNSE. Is that you, sir? You can unmute yourself now. I think you've already unmuted before. My president.
I am.
I'm sorry. So because I know that I've never seen anybody with that name, so it's only you.
I didn't know that.
Yeah.
Yes. So sorry. It is raining cats and dogs in Abuja today, and I happen to be outside at the vulcanizers. I need to fix my tires. So I heard the speaker. He has done well, the presentation, the content, and the delivery of the paper was fantastic. Incidentally, I am a protection engineer, so I know all what he has been talking about. And I just want to give the information that the Nigerian voltage is 400 volts since 1996.
Okay.
The official voltage has been 400 230. But the unfortunate thing is, even in our universities, we are taught with 240.
Yeah.
Because we are using textbooks from the UK.
Yeah.
And we failed to look at our own standards. We had a standard we call the electrical installation regulation and electrical supply regulation called SI5 and SI6, which we popularly call CAP 106.
Yeah.
That was done by the Electrical Division of the Nigerian Society of Engineers with the Ministry of Power and Steel and Power in 1996. So in 2012, the Nigerian Electricity Regulatory Commission reviewed this document and produced it in 2015 and still maintained the voltage of 400 and 230. So it is a harmonized voltage, it is the standardized voltage in Nigeria. So,
Thank you very much.
thank you.
Yeah, I wasn't sure of the dates that happened, but I know, yeah, Nigeria was, even the UK was also using 415 prior to the harmonization, and then
Yes.
they adopted to 400 three-phase and 230 single. Yeah.
Yes.
Thank you
Oh,
very
that's
much.
good. Well done.
Thank you. Thank you.
So can I just take the response, a quick answer to
Yes.
Apollo
Yes.
question? Also, I know it asks about availability versus reliability. Yeah, for how to improve power, it's one of the things that I mentioned. Availability, we have to improve available power at the distribution, at the generation end first, then improve the transmission to be able to carry that available power, then improve on the distribution network to be able to deliver that available power. But as it is just now, based on what is available in the grid or to the local discos, sometimes within that supply, they still lose supply to certain area due to faults. So the power may be available temporarily, but you hear cases of blown transformer. I grew up in Warri. At some point in my area in Warri, there were cases where we had blown transformer for 7 months, and there was a case of 9 months. We forgot until it was replaced. There was available power, no matter how small it was, but because of faulty equipment that was blown, a transformer, and that transformer blew. Now that I've understood, I understood why it blew, because my memory of those sub-distribution substation we have in Nigeria, a transformer, a feeder pillar, and a 11 to 230 lines. There's no proper protection system. That we just have wire fuses on most of those feeder pillars. So they're not giving sufficient protection. Even the protection on the 11 kV supply line, some of them are not properly rated. So transformer get overloaded and they blow eventually. So in that case, the reliability of the system is what failed
rather than
power to that small, rather than the available power.
Thank you very much.
Thanks.
Thank you so much, Victor. I think we would love to continue over, this very interesting discourse. There's even a question in the chat already, but I'm afraid we have to stop at this point to move on to the annual general meeting. I want to thank you for coming. Thank you for your presentation. And we hope that people here will contact you to take this conversation even further. Our friend from the evening power station, feel free to contact the speaker for further discussions. And yes, the presenter can reply via the chat. Yes, you can. Please do check the chat and attend to the question from Engineer Shagun MK, please. We appreciate that. Thanks once again. Thank you. So I'll just stop the screen share. If you could, yes. Right, exactly. And then we'll move on to the second session of this historic day, and that is the annual general meeting of the Nigerian Society of Engineers, Glasgow.